Now we'll look at an interesting application of priority queues that's actually representative of a whole family of critically important applications in applications of computing. It's called event-driven simulation. And the idea is we want to study some property of the natural world by simulating it. And that's something that's very, very common in scientific inquiry nowadays. And this is a very natural idea. And actually, the idea goes back to Einstein. So we want to simulate the motion of n moving particles that might collide. With a priority, this kind of simulation is enabled by priority queues. Without something like priority queues, you couldn't do this for a large number of particles because it would require quadratic time and simply can't be afforded for a huge number of particles. So let's take a look at how we can possibly make this happen. So we use a simple scientific model called the hard disk model, and then this is just for simplicity to get this done in just part of a lecture. Clearly, these things can be extended in many ways. So we're going to have moving particles that either collide with each other and with the walls, and each particle is a disk that's got known position, velocity, mass, and radius. And there's no other forces involved. It gets more complicated if there's more forces, like gravity involved. And this one by itself is very significant. As I mentioned, goes back to study of physics with trying to understand pressure and temperature and Einstein's famous experiment on pollen grains showing that their motion was Brownian or random. So whether it's individual atoms and molecules or it's some bigger kinds of particles, it's a complex dynamic situation that is better understood through computer simulation. And nowadays, that means priority queues. So as a warm-up, here's the code to implement bouncing balls without the collisions. And this is an elementary programming exercise that is the code at the left has the effect shown at the right. So we have a data type called ball that represents just one of the particles and has instance variables that has the position and the velocity. So we make a bunch of them, and then we have a while loop, which is just every 50 milliseconds, clear the whole drawing, and then move the balls a little bit, and then draw them in their current position. And the only thing the move operation does is to update the position of the ball by the velocity, which is just another number, and then it does the bouncing off the walls. If it happens to hit the left wall, you reflect the x-coordinate, and the right wall, you reflect the x-coordinate, bottom and top. You do the same for the y-coordinates. So this is an easy programming exercise given the right display primitives. And it's a good exercise in object-oriented programming showing how just one implementation, then we can use that same implementation to simulate a number of instances. So that's our starting point in terms of the code. So this is the implementation of the ball class. So it's got position and velocity, as I mentioned, and every ball has a radius. And then there's a constructor, and maybe we have a constructor that takes arguments that would initialize the position and the velocity, or maybe initialize them to a random position if there's no arguments. And then here's the move method. And the move method, again, most of the times just takes the x and y coordinates and adds the current velocity times the speed constant, dt, or speed variable that's given as argument dt. And then these tests are for whether it hits the walls, in which case you have to flip the x or y velocity. And then draw is just using standard draw, just draw the ball. So that's all the code for doing the bouncing ball simulation. Now, what's missing in this is what happens when the balls collide with each other. And to cope with that, we need to do both a little bit of high school physics and a little bit of basic computer science. So the physics problem is exactly what happens when two balls hit. They bounce off each other according to some well understood physical process, and that's the high school physics. And the CS problem is how and when do we exactly do these computations for each of the balls, and how can we do it efficiently, that is in n log n time versus quadratic time. Because if we have a computational process that takes quadratic time, then it's not going to scale. We're not going to be able to do large numbers of particles. Simulations of the real world, usually we wind up doing huge amounts of data, and we cannot have a quadratic algorithm. And this is just a first indication of that, of why if you want to do this simulation, you better know about some data structure like priority queues. If you try to do it without it, you're not going to be successful. All right, so let's take a look at what happens. There's a number of things that you might consider trying. One idea is a so-called time-driven simulation. And we just say we're going to update everything every dt seconds. And then we go ahead and do that, and then we could check if there's a collision, if the two balls, some pieces of two balls are occupying the same space. And if there is, then we could roll back time just a little bit and try to figure out exactly the moment at which they collided, and then figure out how their position of velocity should change accordingly, and then continue the simulation. But this has a huge problem. The first one is that you have to check all pairs of balls for overlap. So that's quadratic. So it's going to be really a lot of overall checks. You're not going to be able to do it for a huge value of n. But the other thing is, even if n is small, if you do a very small dt, then you're just doing this calculation over and over again, and there's just too much computation, moving the balls a little bit at a time. On the other hand, if you try and improve things by making dt too large, you might completely miss a collision, as shown in the example at right. So figuring out the value of dt that would really work is a huge problem for the time-driven simulation. Instead, what we want to do is called an event-driven simulation. And this is a very general concept that's useful in all kinds of contexts. And we're only going to change things when something happens. So since the only thing that matters is collisions, we're going to figure that particles move in a straight line between collisions. And what we're going to do is focus only on the times when the collisions are going to occur. And so the way we're going to do that is to maintain a priority queue. And that priority queue is going to have all the possible collisions that could happen in the future, and they're going to be prioritized by time. And when we remove the minimum element from the priority queue, that's the next collision that we have to deal with. And so we have two phases. We have prediction and resolution. So at some time, t, we can take two particles. We know their position and velocity is shown at the bottom here. And we can predict exactly the moment at which they'll collide, assuming that something else doesn't happen to them in between. So then we'll put that predicted collision time on the priority queue. Then later on, when that time comes to pass, we'll be right at the moment when they collide, and we can figure out what to do. Now, there is the possibility that something else happened to them in between, and we'll talk about that change too. So we have to do collision prediction, which is given position, velocity, and radius, when's it going to hit with another particle or the wall. And then there's resolution, which is to figure out how to change the velocities of the particles according to physical laws. Now, This part I'm not going to talk about in that much detail right now because it's high school physics. And so I think most students have had some high school physics and will be able to do this math or at least be convinced that the code that does this math is correct. So if you know that you have a particle that's at a certain position, Rx, Ry, and it's got a certain velocity, Vx in the x direction, Vy in the y direction, then you can, from the distance to the vertical wall, you can figure out how many seconds it's going to take until it hits it. It's basically that distance divided by the velocity. And so that's the prediction. And then the resolution when it hits the wall is just going to change the velocity. So that's you know what the position is. So that's just an example of collision prediction. When's it going to hit the wall? And resolution, what do you do when it gets to the wall? When you have two particles, there's definitely more math. And again, this is high school physics, and we're not going to test on it or even go through the details. But it's just a little bit of arithmetic with the velocities and the positions to deal with what happens how to predict when a given particle is going to collide with another given particle, knowing their velocity and position. So you have to take both velocities and divide their distance by those and so forth. So there's simple formulas to tell us what to do. And we can also figure out the formulas for what we do once they do collide. And again, nobody's claiming that this is easy, but this is the physics part. And it's worked out, and it comes from Newton's second law. And anybody taking high school physics will be able to deal with these formulas. And the rest of us may have to go to our reference book to get up to speed on them. But once it's reduced to code, we can it might have some trouble debugging at first, but at least we can be convinced that it works. But now let's look at the computer science code. So this is just extending our ball data type that we use for the bouncing balls that didn't collide to taking into account these extra things. So ours will have mass, so there'll be some big heavy ones that make things more interesting. And there's also a variable called count, which is the number of collisions the particle's been involved in, and that's useful for a couple of purposes. So we're going to need a bunch of procedures which do the prediction and the collision resolution. Given a particle, what's the time till we hit that particle? What's the time till we hit a vertical or horizontal wall? And the same thing is if we're at the point where we're hitting a particle, what do we do? Same with vertical and horizontal wall. So that's the skeleton. We need those procedures that implement those physics rules for every particle. And this is what they look like. And again, this is high school physics, so we're not going to do it in detail, other than to point out it's really not a huge amount of code. Lots of dx's and dy's and dv's, but really not a huge amount of code. And the other point is we're going to return infinity if there's no collision at all. So that is going to keep that on the priority queue, that event on the priority queue forever. Okay, so that's the procedures that we need, and then there's similar ones for the horizontal and vertical walls. Okay, so now let's look at the main loop for the event-driven simulation. So the first thing is we're going to, for every particle, we're going to compute the next time that it might hit every horizontal and vertical wall. Well, actually, if it's going away from a wall, it's not going to hit it, so that would be infinity. But if it's going towards a wall, then we'll compute the time, and then that's a time in the future. We'll put that event on the priority queue with that time as the key. And then we'll do the same thing for all pairs of particles. So we do have a quadratic initialization phase that we perform just once to get the priority queue filled up. Now, all collisions might not happen. So we might have two particles that are on a collision course, and we're going to predict that point for both of those particles, even right at the beginning. But it might be the case that there's a third particle that knocks one of those out before that thing happens, and that event would be invalidated. So the simulation has to be careful to take that into account, but that's not difficult to do. So here's what the main loop is. So we're going to take the next event from the priority queue. That's the next collision that's going to happen. From all our calculations, there's one collision that's going to happen next. Then we test whether that event has been invalidated. And we do that by using that count field in the particle. So then that tells us what time it's going to be next. So then we have to go through all the particles and change their positions on a straight line trajectory. Where would there be after that much time? Then we have to take the two particles that collide and change their velocities. They bounce off one another. Now those two particles' velocities have changed. Essentially that invalidates the future collisions involving those. And then what we have to do is for those two particles is go through and predict the future collisions with any walls and collisions with any other particles and put all those new events onto the priority queue. But that's it. You got two particles, change their velocities, figure out the future collisions of those particles with the wall, and update the priority queue. And then the main loop is take the next thing off the priority queue and keep going. That's the code that we'll look at next. So we have a bunch of convections just to reduce the code. And if we have this thing called event, which involves, it says between two particles something is going to happen at a certain time. And we're going to adopt the conventions that if neither particle is null, then we're talking about two particles. If one of the particles is null, then we're talking about a wall, a vertical or horizontal wall. And if both particles are null, we're saying we just want to redraw things. That's a bit of a hack, but it cuts down a lot of code. Our compare to is by time. And then, again, we need an is valid to check about intervening collision. And then here's the skeleton of what's going to happen with the collision system, which is the key thing is this prediction method that takes a particle as argument and adds to the priority queue all the possible collisions involving this particle. So it's going to go through every particle and call the time to hit method for that particle, and then it'll put an event on the priority queue for that time, this particle with that particle. And then it'll also put an event for the vertical wall and the horizontal wall, again using this null convention to say that the event second argument null is vertical, first argument null is horizontal. So that's a key method that gets used in the simulation for each of the two particles that are going to collide. So now we can look finally at the main event-driven simulation loop. So there's build the priority queue. There's do this prediction for every one of the particles. And then also we're going to put as the first thing to happen always an event that says redraw everything. So that's just a way of making sure that the simulation keeps proceeding. It's an easy way to get things drawn. Okay, so now the main loop is while the priority queue is not empty, we're going to pull off an event. We're going to test whether it's valid, and that's to just check if anything happened with those two particles. We're going to pull off the two particles. And then we're going to move all particles by the amount of time that has elapsed since the last event. And then we're going to test which of the 4 types of events that it is. It's either redraw, bounce B off A, or bounce off a vertical wall or horizontal wall. And then we'll go ahead and do the predictions of each of those particles, A and B, against all other particles. That's pretty much all the code for the simulation. So this is data-driven code. So one thing we can do is just run it for 100 balls in random position at random velocity. But what's nice about data-driven code is now that the code's working, and again, we're not saying this is trivial code to write, but it's definitely manageable, and it's enabled by priority queues. Without priority queues, it would be quite a bit more complicated to figure out how to do this, and also it wouldn't be reasonably efficient at all for large data sets. So that's a simple simulation, just generate random positions. People might be interested in this one. Now, this isn't exactly precisely what would happen in the real world, mainly because we didn't put in the simulation what happens when 3 particles are touching, or there's 2 touching and another one hits them. And also, nobody racks up a set of billiard balls such that all 15 are touching in all places. So life can be complicated when you're trying to simulate the natural world. This is a little bit about Einstein's experiment. If you got one big particle like a pollen grain and lots of little particles like atoms, molecules bouncing against it, the big one is going to move about randomly. And then this is another famous physics experiment showing diffusion. There's many other things that you can do with this basic collision system. If you have huge numbers of particles and you measure the number that hit the sides and the frequency with which they hit the sides, you can do experiments relating temperature and pressure and many other things, or do 3-dimensional versions. Again, simulation of the natural world is an increasingly important application of computing. And you need efficient data structures like priority queues to get it done.